My name is Chris Stevens. I am a senior lecturer in applied mathematics and the co-leader of the Gravity and Cosmology Research Group at the University of Canterbury. So my research is in gravity, in particular the best theory of gravity we have so far, which is Einstein's general theory of relativity. This is a very interesting theory in that it represents gravity as a geometry, and the effects of gravity that we feel on Earth are not due to a force but due to a curvature in this geometry. This is a four-dimensional geometry that combines both time and space into one continuum that you might have heard in your favorite space movie. So what I'm very interested in is a consequence of this theory called gravitational waves. So if you had very big objects in the universe like black holes or neutron stars where gravity is very strong, if they collide, they can produce these big waves in this geometry that travel at the speed of light. And we can actually now detect them here on Earth with laser interferometers. This can allow us to understand some properties of the system that caused these gravitational waves. So if you want to understand how these gravitational waves propagate and their properties, there's quite a few things you need to know. You need to know about the geometry, because they are essentially in the geometry of our space-time. You need to know differential equations, which are the governing equations to explain how these waves propagate. And you also need to know some numerical methods in order to approximate solutions to these equations on the computer. Because in general, you're going to have a situation that's too complicated to be able to solve it with just pen and paper methods. So once you've got all of this, you can understand certain properties of gravitational waves, such as how they scatter off a black hole, how much energy is transferred during this process, things like that. Here, one of our main research objectives is to utilize a specific type of mathematics called conformal transformations. So in general, if you're wanting to understand, for example, how gravitational waves interact with the black hole, the idea would be to put a black hole in an empty universe, shoot a gravitational wave at it, and then see what happens in the future. There is a technical caveat to this, which is that you have to do this, shoot this gravitational wave in from the infinite past and see what happens at the infinite future. And you can imagine that having infinity in your calculations is a bit cumbersome. So what we can do is we can actually use these conformal methods to squish our space-time into some finite picture, and then utilize that to be able to study this problem from a local perspective. And this is a very novel approach that hasn't really been applied yet, and that's part of the research that we're doing here at the University of Canterbury. I really love my research, and I hope that you found this enjoyable as well.